Hi, have you ever had a topic in any subject that it was very, very easy for you or very, very hard for you? And after you see it, you watch it and work on it, you notice that you didn't use it again in your life? Yes, sometimes happens, yeah? For example, for some people, factoring is one of these topics. Pythagorean theorem is other of these topics. However, let me tell you that even that you were very good in that, or weren't a good guy on this topic in particular, the fact that it was easy or hard for you defines something that makes you have some behaviors that you have right now. Yeah, if you don't believe on me, you don't trust me, just do the experiment. Ask about any topic that you don't use anymore, but it was really easy or really hard for you, and notice how these people behave. Maybe you will notice that people that says that is hard have some behavior that is related, and people that is good on it have some behavior related that that it's that they used. Okay, and I'm telling you this because mathematical induction for me is one of these topics. It's a topic that maybe you're going to study once in your lifetime, and then you're not going to listen about this anymore. But something that I'm pretty sure that is going to help you is the fact if you found it easy or hard. This is going to determine some of your behaviors in life. So let me explain you the mathematical induction, how it works, and you will see that mathematical induction is a topic that it's like, to me, is when you finished all your math introduction, mathematical induction is like the top, because you're going to use many information that you had during algebra. That's pretty good for mathematical induction. So, first, if it's easy for you, so let me tell you that your abilities in algebra are very good. Now, if you think that it's really hard, maybe it's not because of mathematical induction. It's because there is something in math that is not clear for you. And if you think that is important for your life, you need to study that. Mathematical induction is so easy. Principle of mathematical induction is just the things you need to know. First, the statement is true for n equals 1. So you have to check if some equation or statement is true for n equals 1. Second, if the statement is true for some natural number n, it is also true for some natural number for the number n plus 1. Okay? So if you check it for n, you say that is true, you check it for n plus 1, and it should be true as well. And finally, if both conditions hold, the statement is true for all natural numbers. And then you prove by induction. Now we're going to see it with an example. This is a typical example in which we use mathematical inductions to show that the following statement is true. You can see the statement here. This is the statement. It's a sum, and you have an equation to prove it. Okay? So we're going to check first the steps. Check statement number 1. Check if it is true for n equals 1. Okay, for n equals 1 means that the sum just starts with the first term. Okay, 1. So the left side of the equation is 1. and this is equal to the right side of the equation for n equals 1. Okay? So let's see if it's correct. 4 to the first power, okay, this is 4. 4 minus 1, this is 3. And 3 times 1/3, yes, essentially is 1. So statement is true, or it's better to say condition 1 holds. Okay, condition 1 holds. Now check condition number 2. There are many ways to prove the statement by using condition number 2. I prefer to use summation notation. If you don't like to use summation notation, so you can watch other videos that uses another ways to express it. Okay? But let me show you how I use it by summation notation. So the left side of the expression is a sum. You can see that is 1, 4, 4 to the second power, 4 to the third power, and until 4 to the n minus 1 power. So using summation notation, it will be the sum from k equals 1 to n of, so 4 to the k minus 1 power. 4 to the k minus 1 power. Usually in this type of sequences, it's easy to know the n term because it's the last that you see. So here is 4 to the n minus 1 power, so we got to transform into k because k is the counter. And this is equals to the right side. The right side. Okay, so assume that the last statement is true. Okay, so this statement is true. If I have this sum, I will say that is true. Now, use n equals n plus 1. Okay, so now we're going to write the same equation, but we need to prove that the statement is true for n plus 1. Okay, so if the statement is true for some natural number n, we said that this is true, so it is also true for the natural number n plus 1. So should be true if I change n for n plus 1. So I'm just going to copy, and I'm going to change all the n's by n plus 1. And here, n plus 1. Okay? This is how we're working. But the sum until n plus 1 is the same as the sum until n plus the sequence for k equals n plus 1. Okay, so the sum until n plus 1, this sum is the same as the sum until n plus the sequence for n plus 1. n plus 1. Now maybe you have noticed that we're using a lot of algebra here, a lot of information. So for example, if you don't understand pretty good about these sequences, check the video about sequences and how to find sums, in which there's an explanation of how to use summation notation a little bit. And if you don't understand, send me an email. Send me an email, tell me in your comments, I need to know how to apply summation notation, and I'll explain you. So we have here that the sum until n plus 1, okay, this sum is the same as the sum until n, so I'm going to copy the equation. This sum is the same as the sum until n, I mean this, plus the sequence for k equals n plus 1. So the sequence, oh my god, the sequence for k equals n plus 1. Okay, you can see here that n plus 1 minus 1, so 4 to the n power. Use your assumption. What is our assumption? What is the assumption? Okay, our assumption is this, that the sum for n, or for any number n, the condition holds, the statement is true. So 1/3 factor of 4 to the n power minus 1. So I'm going to use the assumption here. So I have this sum that is the same that this sum, so should be the same as this expression. 1/3, 4 to the n power. That's it, minus 1. Okay, so we have to show that this side of the expression is equal to this side of the expression. Some students start doing things, algebra and stuff, to understand how to prove that the left side of the expression is equal to the right side of the expression. But here is when you use the equations and how to use equations. And as we have exponents, you're going to use exponents. So you have to use many topics here. Many topics. You will see if you understand the topics. This is why you work on mathematical induction. If it's hard for you, you have some topic that you don't understand. So what I usually do if I have a fraction, equations, we can read of fractions. So multiply equation by 3. Okay? I'm going to multiply the equation by 3 to read of fractions. No? You don't like fractions? This is one way to read of fractions. So what if I multiply 3 times 1/3 of 4n minus 1? This 1/3 is gone. And here 3 times, don't forget this 3. Some students forget to multiply each term. When you say multiply the equation by 3, you're multiplying each term. So 3, and here we have 3 times 1/3, so goodbye. So essentially we have this expression. Okay, lucky that the parenthesis is not needed. We have to prove this equals to this. Okay, some students have problems in this process. So I'm just gonna tell you, okay, use algebra, use addition of polynomials. If I have 4 to the n power plus 3 times 4 to the n power means that here I have 1 time and here I got it 3 times. So this just means 3 plus 1, 4. 4 times 4 to the nth power. And now properties of exponents. What happens if 4 to the first power, 4 is 4 to the first power times 4 to the nth power? Exactly. You have to add exponents. 4 to the n plus 1 power. If you don't understand how to do that, you need to check your algebra operations. You need to check addition of monomials and polynomials, and you have to check properties of exponents. Now notice we have that the proof we did is correct. So a statement is true for n plus 1. Okay, statement is true for n plus 1. Therefore, the condition 2 holds. Okay, so we found that condition number 1 holds. We found that condition number 2 holds. So what is the conclusion? If both conditions hold, the statement, I got my Spanish, the statement is true for all natural numbers. So now this statement is true for all natural numbers. Okay, as a conclusion, really, applying mathematical induction is not hard, okay? Because it's just 3 lines, easy to understand. If it's true for n equals 1, and if it's true for n, so check that it's true for n plus 1. So it's easy to do it. However, if there is something that is not clear, maybe it's because you need to check another topic. It's not hard because of mathematical induction. Maybe it's hard because you don't know some topics. And you cannot build an empire by using something that is not appropriate to build an empire. Okay? So if you want to understand mathematical induction, just check maybe if you don't understand some steps to apply. I hope for your comments. Anything that you need to say, tell me. I'll make the better to improve. I will help you in anything you need. And that's it for today. Goodbye.